Acid-base reactions were among the first concerns of modern chemistry. Antoine and Marie-Anne Lavoisier kick-started the chemical revolution in the late 18th century by rechristening a gas discovered by Jason Priestley to oxygen, or acid forming. For the Lavoisiers, every acid was created by a combination with oxygen. Bubbling oxygen through different liquids turned them acidic, as did the oxygen-rich carbon gases, carbon monoxide and carbon dioxide. This became such a dogmatic point that it delayed the acceptance of chlorine as a separate element by years. They knew that it could produce chlorine gas from muriatic acid, but they thought that it should have contained an oxygen, and some undiscovered muriatic radical. Now we know that they could not find the compound they expected because their theory was too limited. Muriatic acid was really hydrochloric acid, and contained nothing but a chlorine atom and a hydrogen atom. Nearly 100 years later, Svante Arrhenius nearly rescued the Lavoisiers with his acid-base theory, one that we still apply to aqueous solutions. An Arrhenius acid is any substance that gives a hydrogen ion to water to create a hydronium ion, H3O+, or causes an increase in hydronium concentration. An Arrhenius base is any substance that takes a hydrogen ion from water to produce a hydroxide ion, or any substance that reduces the concentration of hydronium, since hydroxide plus hydronium makes 2 equivalent moles of water. So acids in the Arrhenius theory still depend on oxygen, but on the oxygen found in water. Now muriatic acid, or hydrochloric acid, was no longer a problem. The chlorine and hydrogen would dissociate in water to produce HCl plus H2O, turning into a chloride ion and a hydronium ion, giving up a hydrogen to water to increase the concentration of hydronium, therefore acting as an Arrhenius acid. Similarly, dissolving what they called soda ash and what we call sodium carbonate in water caused the salt to dissociate into sodium ions and carbonate ions. The carbonate can then undergo a reaction with water to produce bicarbonate and hydroxide. Taking the hydrogen from water increased the concentration of hydroxide, therefore acting as an Arrhenius base. We can even do that again with the bicarbonate in water to produce carbonic acid and hydroxide. But for reasons we'll discuss later, that reaction is going to run forward and in reverse to produce an equilibrium. In the reverse case, we have carbonic acid and hydroxide converting into bicarbonate and water. In acid-base chemistry, we'll always find that a molecule forms a conjugate pair. Carbonic acid is the conjugate acid of bicarbonate, and bicarbonate is the conjugate base of carbonic acid. Water itself is an interesting case because it can and does spontaneously ionize itself, acting as both the acid and the base. So water plus another water can create hydronium and hydroxide. Although it really was a revolution for acid-base chemistry and for electrochemistry, as we're going to see in a later session, Arrhenius's theory couldn't save the oxygen theory of acids. Even though a lot of acid-base chemistry is done in water, we can conceive of something as acidic or basic without water. For example, we could perform all the same functions in ammonia solution. So HCl plus ammonia, converting into a chloride ion and an ammonium ion. Here, HCl is still an acid, with chloride as its conjugate base, and ammonia is the base with ammonium ion as its conjugate acid. Arrhenius's theory of acids and bases was really the only game in town for about 40 years, until almost simultaneously, Johan Bronsted in Denmark and Thomas Lowry in England developed this new idea. So we call it the Bronsted-Lowry theory. Here we focus only on the donation and acceptance of the proton, the hydrogen ion. The protonated molecule is the conjugate acid, and the deprotonated molecule is the conjugate base. A Bronsted-Lowry acid-base reaction is between two conjugate pairs. In water, both bicarbonate and ammonia are bases. In Bronsted-Lowry theory, we could write bicarbonate plus ammonia turning into carbonate and ammonium, and find that the bicarbonate is acting as an acid. But does this actually happen, or should we instead write bicarbonate, and ammonium, turning into carbonic acid and ammonia, where bicarbonate is the base and the ammonium ion is the acid. To answer that question, we need to know something about the relative strengths of acid-base pairs. We'll discuss that next time.